Hello and good day everyone. So in this video, we would be discussing about seismic load analysis using static force procedure as per NSCP 2015 standards. So in this video, you would be using the term seismic load a lot. And in a nutshell, when we say seismic loads in the case of our video, it is the same as earthquake loads. So again, in the context of our video, seismic loads and earthquake loads are practically the same. Mas astig lang yung seismic loads pakinggan. Kaya yun yung gagamitin natin, no? Okay? So when we say seismic loading, it is basically the application of an earthquake-generated agitation to a structure. So when we say agitation yun, basically nag-shake siya. So if we would be subjecting shaking onto our building, that is already earthquake load or seismic loading. So as you can see in this GIF right here, so as the building is shaking, of course, it is moving, and since it is moving, it is subject to different kinds of damages. So it may crack, it may twist, and the like. So as structural engineers, our goal is for the building to withstand those forces and not to fail during the earthquake generated agitation. Okay? So when we say earthquake load or seismic load, it is a dynamic load, meaning that it is moving as it brings about vibration of the structure. Okay, so that is for the introduction for seismic loading. So in this series of videos, we would be hearing the terms base shear and story shear a lot. Okay, so what are those in the first place? So for base shear and story shear, so suppose that this structure here is the building that we are to analyze. And again, so suppose that in this building, we are now to subject it with earthquake. So whenever that there are ground shaking or earthquakes, the tendency of the building is that it would be swaying. So exaggerated, but for example, that in this building here, it would now sway to the left. This is now what it would look like. Okay. Again, this is exaggerated. I hope that your building will not sway this much. But again, just for the sake of our lecture, I have exaggerated it. So what caused this building to sway in that direction? Okay, so a little bit of a background or a little bit of a review from your physics class before. Suppose that we have a certain object. So suppose that this here is a box. Okay, so this box will remain at rest, meaning that it will not move unless an unbalanced force will be acting upon it. Okay, so suppose that we would be having a certain force here, which is basically equal to the force due to friction. From that, it still wouldn't move, meaning that in this case, the summation of forces is equal to 0. So meaning the forces are balanced. Okay? But for example, that this force here would be very large. And from that, the summation of forces is not equal to 0. From that, guys, it is not balanced any longer. And if it is equal to, if it is not equal to 0, so it must be equal to something. So what is that something? So if it is not equal to 0, the summation of forces is now equal to mass times acceleration. Okay, so this is now the unbalanced force. Okay, so going back to our structure, so in order for the building to move, so there must be an unbalanced loading acting upon it. Okay, so those forces, so let me just draw some forces here. These forces here would be called the story shear, whereas the story shear is equal to mass times acceleration. But I just realized ang pangit ng drawing ko. Dito na lang tayo sa generated. Okay? So, these arrows here are what we would be calling story shears. Okay? So, as you can see that they act on individual stories and that their magnitudes differ. Differ, I should say. So, they differ depending on the floor. And how do you solve for this story shear? So basically, again, guys, if this is mass times acceleration, so for the value for the mass, that is the weight of that particular floor. And for the acceleration, also that is the acceleration that is being experienced in that particular floor. Okay, so mass times acceleration. And as you can see here, guys, so suppose that in our example, for every floor, let's suppose, this is just for example, that all of them would be having the same mass. So again, for example, that the mass would be the same throughout. Even though that the mass will be the same throughout, they would still have different magnitudes because per floor, the acceleration differs. Okay? So the tendency is that the top floor of the building would be the floor that would be having the greatest acceleration. So if you would be going back to our previous GIF, if you would be comparing the movement at the top floor to that of the lower floors, the top floor would be the one having the greatest movement. Thus, it would be having the greatest acceleration. Okay, so going back to our slide here. Okay, so that is the reason why, even though, for example, that per floor they would be having the same mass, the story shear would still differ. And from that, guys, the top floor would have the highest tendency that it would be having the greatest story shear because of that comparison. Okay, and if this is the only force present, which is the story shear, the tendency of this building is not to sway. Rather, it would now be moving towards this direction. Okay, but since the lower columns would be embedded into the ground, so as you know that we would be embedding it into the ground for us to connect it with the foundation, we would now be having a horizontal support reaction at the level of the ground or the base. Okay, and from that, guys, if we would be solving for the resultant or for the support reaction or horizontal support reaction at the base, that is what we would be calling the base shear. Okay, so with that analogy, we could now say that the summation of story shears, so story shear, that is basically equal to the base shear, since the base shear is basically the support reaction. So from that, guys, the base shear would result from the presence of the story shear. Okay, so how could we now solve for the base shear? Oh, by the way, this is what would happen with the building with the presence of course, the base shear. So it would sway. So the building would sway, except, of course, for the base. Okay, so once again, how could we solve for the base shear? So we have plenty of ways in solving for the base shear, and as seen in the title, we are particular with the first one, which we call the static force procedure. So before we proceed with static force procedure, let me just introduce the others. So for the second one, this is to be called the simplified static force procedure, and as you can see here, this is just method A, which is simplified. So as for these two, as for the static force procedure and simplified static force procedure, they are rather approximated. Okay, meaning that it is not really that accurate, but it is still acceptable according to the code, depending upon their structure, of course. Okay, so the third one is what we would be calling the dynamic analysis using RSA, or response spectrum analysis. So response spectrum analysis. And for the fourth one, this is now the dynamic analysis using time history analysis. So time history. Okay, so these two here are rather much more advanced than that of the first one. However, guys, for the dynamic analysis, these are the most accurate or the most precise analysis if you would be solving for the base shear due to earthquake. Okay, so a little bit of background between these two. For response spectrum analysis, if you would be making use of this procedure, you would now be solving for the maximum response. So max response. Okay? But for the dynamic analysis using time history analysis, instead of you just solving for the maximum response, you are actually solving for all responses per time. So for example, nag-earthquake ngayon. Then as you know that for a particular earthquake, it would last for how many seconds? So in time history analysis, it will now generate the response of the building for every second or for every, let's say, 0.01 second. So from that, you can now see the behavior of the building for every time period, or I mean for every time. But for response spectrum analysis, you are only particular with the maximum response. So I'm actually planning to make a video about this too. But then again, in this video, we would be solving for the Bayes shear using static force procedure. Okay? So what are the different factors that would be affecting earthquake or seismic loads? So the first factor that would affect the load is the type of structural framework or the type of structure. If let's say your building would be having beams and columns, and let's say that if you would be comparing it with another building, same height, same mass, but it would be having a different system. So suppose that it is full of shear walls, their seismic response would differ. Okay? So the Bayes shear would differ between the two. So the stiffer the building, the more Bayes shear it would absorb. Absorb, I should say. Okay? Next is the distance to the seismic source. So I think this is rather self-explanatory. So here in the Philippines, the seismic source that we are talking about here are the fault lines. So fault lines. Okay? So if let's say the structure is near a fault line, meaning it has a tendency that the building will be absorbing a greater magnitude of earthquake. So suppose that the building is far away from a source line or a fault line, then meaning that it has a lesser tendency that it would be absorbing a greater magnitude of earthquake. Okay? So also, another factor is the capacity of the source. So we have different fault lines here in the Philippines. So these fault lines would differ in strength. Some fault lines would be stronger than that of the others. Okay? So another factor that would affect the earthquake load is the site classification or the soil type. So as you know that for a particular building, it will be on top of earth. And wherever you are here on earth, the soil property would differ. Some soil would be very stiff, some soil would be very dense, some soil would be very soft, some soil would be very let's say mushy and again soft. Okay, so those would also affect the building itself or the response of the building in terms of earthquake. Okay, so also the structural period, when we say period, this is let's say a unit to measure the time it would take for a particular building to vibrate. So later on that. Okay, and also guys, the weight of the structure would affect, of course, the Bayes shear. As you have heard earlier, that these story shears would be mass times acceleration. Where would we get mass? That is basically the mass of the structure, and the mass multiplied by gravity, that is basically the weight. Okay, so for letter F, that is weight of the structure. And for letter G, lastly, the importance of the structure. I have indicated a question mark here because in real life, this won't really affect the Bayes shear per se, but rather this is a rather factor of safety. So meaning here, let's say that the building that you are building or that you are constructing is very important, for example, hospitals, evacuation centers, you would be applying some factor of safety onto it para syempre pag masisira man yung building or kaya knock on wood, if let's say calamity strikes and then buildings would now be falling down, those buildings or the essential buildings should be the buildings that would still be standing. Okay? So How can we now solve for the base shear using static force procedure? It is rather straightforward. We would just be making use of these equations here. Mas madadali lang naman po. Just memorize this base shear formulas and just know how to get these values. So it is rather straightforward. So for these variables here, which is enumerated on this side of the video, so they would represent these factors. Okay, so exhibit A for the value for R. So for the value of R, that is the type of structural framework. So for the value of T, this is again the structural period. The value of I, that is the importance factor, and so on and so forth. Okay, so basically that is just how we would be solving for base shear using static force procedure. But let me just enumerate these variables one by one and how we would be knowing them. So first up, let us discuss the importance factor. So for the importance factor, this is once again rather straightforward. You would just look at this table here, table 208-1. So for essential facilities, the value of I is 1.5. Hazardous facilities 1.25, and if it is not the two of them, then meaning that it is 1.0. So for essential facilities, it includes the following but are not limited to. So we have um, fire stations, police stations, garages for emergency vehicles, aviation control centers, public school buildings, hospitals, and the like. And for hazardous buildings, as you can see at the bottom part, so these are occupancies or structures housing or supporting toxic or explosive chemicals or substances. So some example here are that of um, power plants, let's say factories for fireworks, and etc. Okay, so I would not discuss the occupancy 3, 4, and 5 in detail since in our topic, it won't really matter if it is 3, 4, and 5 since all of them would be having the same importance factor. So my clue here is for you to memorize the essential facilities or the inclusions for essential facilities and that of hazardous facilities. And if the structure is neither those two, meaning the importance factor would just be 1.0 regardless if it is 3, 4, and 5. Okay? Next up, so going back here, let us now discuss the response factor. So for the response factor, it would differ once again in the type of building or the type of structural framework that you are rather building. So we have two tables in NSCP. We have that of the response factor for concrete, and we also have one for steel. Okay, so for concrete, just for example, if for example that you are building, let's say, an ordinary reinforced concrete shear wall building, meaning that the value of R would be 4.5. So it is actually as simple as that. But take note, guys, that these systems here would be having their own limitations. So of course, all of them would be having other limitations. And from that, guys, we have here provisions that some of them would be not permitted for a particular zone, and some of them would be permitted for a particular zone given a particular limit. So let us have this for an example: cantilevered column building system. As you can see here, that the value for the for the value of R is 2.2. So that is the value that we will be using. But take note, guys, that according to this two columns here, if the building is in zone 2, which I will explain later on, it is indicated here that it is NL. Meaning by NL, that is no limit. Meaning if you would want that to be the framework of your building, you could have a building height of, let's say, more than 100 meters, 200 meters, since it has no limit. Okay? But if the building is to be constructed in zone 4, it is only limited to 10 meters height. Okay? So you could not make use of that system if the building is, let's say, 10.1 meters. Okay? Or let's say 11 meters, 12 meters. So, aside from NL and the number, we also have NP here. And by NP, it means no problem. I mean, it does not mean no problem. Rather, it is the opposite of that. NP stands for... Ano ni NP? No, pare. Na-joke lang. Ano na yung NP? Not permitted. Apologies. So, NP stands for not permitted, meaning that for the build or for the frameworks here with NP, meaning you cannot use them in Zone 4. But what is Zone 2 and Zone 4? So here in the Philippines, we are divided into two zones, namely Zone 2 and Zone 4. So as you can see, Zone 2 includes Palawan, Sulu, Tawi-Tawi. So yun na lang, review nyo na lang ulit yung HECAS nyo dati. Just check if your building is located here, meaning that it is Zone 4. And if your building is located here, meaning that it is Zone 2. But why not 3 and 1? Bakit walang 1 pati walang 3? Well, ganun lang po kasi talaga. These zones here are the peak ground accelerations. So meaning that for buildings or for buildings in zone 4, it is actually being expected that the peak ground acceleration is near 0.4 gravity. So if you would be multiplying that is 0.4 times 9.81. So the maximum ground acceleration is around that value. But for Palawan, Sulu, Tawi-Tawi, that is 0.2 G. So, bakit wala pong 0.3 pati 0.1 sa Pilipinas? Wala, di po natin talaga control yung bagay na yun. In some other countries, they have 0.1 G. In some other countries, 0.075 G. And in some countries, 0.3 G. Just not here in the Philippines. Okay? So, going back, asan na pa tayo? So, response factor. Okay, so, again, for the response factor, just choose for the necessary value for R. Okay, so we have for concrete, we also have for steel, which is rather 2 pages. Okay, then also we also have the near source factors NA and then NV, and then for the seismic coefficients CA and CV. Okay, so let us proceed to CA and CV first. So for CA and CV, they are dependent upon the zone. Once again, we have two zones here in the Philippines, which I explained earlier. And it is also dependent upon the soil profile type. Okay? So for the soil profile type, we have SA, B, C, D, E up until F. And what are those? So basically, we have a separate table on that. So these are now the different soil profile types. So SA for soil containing hard rock, matigas na bato. SB, rock. SC, very dense soil and soft rock. SD, stiff soil profile. SE, this is for soil, soft soil profile. Okay, so how would you know which soil profile your building would be having? So the best answer to that is for you to ask your geotechnical engineer. Okay, so if you do not have a geotechnical engineer, my best advice to you is for you to get your own geotechnical engineer. Okay, so what are the basis of your structure, of your geotechnical engineers? So meron po tayong mga basis dito. So we have the shear wave velocity, we have the standard penetration test, and also the underrange shear strength. So for shear wave velocity, this is how fast the wave travels from one point to another. So suppose that this is the ground, and let's say a vibration happens here, or let's say vibration happens here at the fault line. So if vibration happens, the wave would now travel, and well, basically that is now the shear wave. Okay, so also delete ko na lang, medyo wala pa naman akong background dun sa shear wave velocity, kaya dun na lang po tayo dun sa pangalawa dito, which is the SPT. SPT stands for standard penetration test. So when we see standard penetration test, ayun, ang tendency po niyan is that, for example, that we have here a material, in some cases split spoon and the like, pupukpukin po yan ng napakabigat na material, in some cases 70 kilos, I think, or 70 pounds. Wait, I'm not sure. Confirm ko nga lang. Okay, so according to Gemini, so that is 64 kilos, I should say. So approximately 140 pounds. So, ayun po. Pupukpukin po yan with the height of 760 mm na height. So the hammer will be elevated at a height of approximately 30 inches. Then it will be dropped. So free falling body. And ayun. So for example, that the soil, oops, sorry. So for the soil, if it would now be penetrated by 300 mm, you would now be counting the number of blows it took for it to penetrate the soil by 300 mm. Okay, and you also have on-the-range shear strength here in terms of kilopascal. So those are now the basis of our geotechnical engineers. Okay, so next up, going back here, for the near source factor, as you can see here, as the name would imply, it is a factor that is dependent upon how close the building is to the nearest seismic source, which is once again the fault line. Okay, so if it is less than 2 kilometers, we would be making use of this column. If it is less than 5 kilometers but greater than 2 kilometers, we would be making use of this column here. And if it is greater than 10 kilometers, we would now be making use of this particular column here. So suppose that the building is, let's say, located 8 kilometers from the nearest fault line, then as you know that between these two, it is somewhere in between. So if it is somewhere in between, you would now be interpolating. Okay, so you would be interpolating. So aside from these columns, it is also dependent upon the seismic source type. So here in the Philippines, or not really just here in the Philippines, but for the seismic source type, we have three. We have A, B, and C. Okay, so what do those imply? Okay, so for seismic source type A, these are fault lines that could produce magnitude 7 up until magnitude 8.4 earthquakes. Okay, for seismic source type B, these are fault lines that would produce magnitude 6.5 up until 7 earthquakes. And for seismic source type C, these are fault lines that would produce less than magnitude 6.5. Okay, so how would you know in the first place? So one thing that you could do is for you to research on the net. Let's say that your building is located near the West Valley Fault, which is in Manila, and there you could actually search in the net or in PHIVOX what is the maximum magnitude that is not intended but rather anticipated in that fault line. Or you could also make use of this empirical formula by Wells and Coppersmith, whereas the magnitude of the earthquake, or the expected magnitude of the earthquake, is equal to A plus B, and these are the values of A and B, times the logarithm of L base 10. So for the value of L here, that is the length of the fault line. Okay, so in this case here, if you are, let's say, solving for the magnitude of the of the valley fault system, which is this fault line here, you would now first measure that. Okay, so you would measure the fault line, that is the value of L here already. So take note that the value of L must be in terms of kilometers. And also, you must know its fault type. So would it behave in a strike slip manner, in a reverse manner, or in a normal manner? So all fault lines would differ, no? So depending upon the fault line, you should know the fault type. Okay, so let us have a little bit of a background about those fault types. So we have here the strike slip fault, that is the first one, the reverse, which is this one here, and the normal, which is at the middle. So for the strike slip fault, as you can see here, it is rather sideways. So suppose that this here is the fault line. Sorry. So this is here is the fault line. So the behavior between the two lands, or the two planes on the opposite sides of the fault line, it would now be behaving in this manner. For a normal slip, this will result from the tension of the two lands separating the fault line. And as for the reverse slip, this came from a compressive force, or for compressive stresses. So as you can see here, guys, if you would be stretching this, or if you would be applying tension forces for the hanging wall, it has a tendency that it would slip down. Okay? So dudula siya pababa kasi nga hinihila siya. But for reverse slip, since the force is actually compression, the tendency of the hanging wall is that it has a tendency that it wants to go on top of the footwall. Okay? So that is the difference between normal slip and reverse slip. Once again, for normal slip, this is rather tension. So if you would be stretching it, the tendency of the hanging wall is that it would slide down the footwall. But if it is reverse slip, the tendency is that the hanging wall would now have a tendency that it wants to go on top of the footwall. Okay, so solving for the magnitude, you could now solve for the magnitude once again. Solving for the magnitude, you could now see what the seismic source type is, and from the seismic source type, you could now solve for the values for NA and NV. So going back to our previous formula. Ano yung formula na yun? So for our previous formula, so we have already discussed CV, R, I, CA, NV, IR. So as for the value for Z, once again, it is basically this one here. So this is the values for Z. So for the value for Z, that is 0.2 for zone 2 and 0.4 for zone 4. Okay, so next up, the value for the structural period. Okay, so what is a structural period in the first place? Teka lang, let me create another slide. So before I discuss this formula here, so what is structural period? So when we say structural period, where's my pen? This is the time it takes for one cycle of vibration. Okay? So suppose that we would be having a pendulum. So I think you already know what a pendulum is. So ito siya. And let's say that we would be applying a particular force towards this direction. So the tendency of this pendulum is that it would be swaying to this side. Then after swaying to that side, it now has a tendency that it would return, but of course it would go to the other side. Okay? And from that, guys, it would go back to its original place, but of course, it is just not one vibration, no? So paulit-ulit po 'yan, okay? But for a structural period, we are only particular here for the time it takes for one cycle. So this is basically one cycle. So going to the right, going to the left, and going back to its original position, that is now one cycle of vibration. Okay, so what is its relation to a structure? Okay, so if I am to erase this first, okay, so suppose that this building is once again subject to earthquake, and due to earthquake, story shear would happen. So magkakaroon po tayo ng story shear. And for example, given those story shear, again, the tendency of the building is that it would be swaying to one side. So exaggerated, it would be swaying to this side. And after swaying to that side, the building has a tendency that it wants to go back to its original position. So if it's swayed to that direction, then maybe, not just maybe, the building, by virtue of its self-inertia, it wants to go back to its original vertical position. So it would apply, or itself would apply a certain force to itself to go back to its original position. However, sobra pa rin yan. Sobra po siyang ganito. Okay? So it would go back here. I not really go back, pero nga sobra nga siya. And since sumobra na naman siya, it still has a tendency that it wants to go to its original position. So if let's say that we have this particular pen here, if I am, let's say, to push this towards this direction, the tendency of it is that it would vibrate. I would just exaggerate the movement, is that it would vibrate in this manner up until it stabilizes. Okay? So from that, guys, this is one vibration, whereas it moved to this direction, then it has moved to the other direction, and ultimately it would go back to its original position. Okay, so once again, structural period is the time it takes for one cycle of vibration. Okay, and a little bit of a trivia. So what is the relation between period and frequency n? Okay, so once again, T is period, n is frequency. So what are the relations? So when we say frequency, this is the number of vibrations per second. Okay? But for period, that is the number of seconds per vibration. So as you can see here, guys, they are inverse. And from that, we could now say that they are inversely proportionate, and basically the period is the inverse of frequency and the other way around. The frequency is the inverse of period. Okay, so how can we now solve for the structural period? We have three known methods. We have method A, which is just, I mean, this is the easiest. However, this is just an approximation, meaning that this has the least accuracy between the methods I would be telling you. Then aside from that, from method A, we have method B. So we have Rayleigh method. And this is the formula that you will be using there. And the third one is rather the method that would give the most accurate method in you predicting the period of the building, and that is by making use of eigenvalue extraction method. Okay, so if you would be making use of the where is that? If you would be making use of the dynamic analysis, regardless if it is RSA or using THA, the best method for you to use is that of the eigenvalue extraction method. Nasaan na naman yung slide ko? Eigenvalue extraction method. Because once again, this would give you the most accurate period. As you can see here, guys, that for method A, so method A is basically equal to CT, whereas CT is equal to these values here. And HN is the height of the building. Okay? So CT times HN raised to 3/4. As you can see that those are the only two what do you call this? Values here. Only one being the variable. So ito lang po yung nag-vary, which is HN. And from that, since in this equation, so suppose na nakapili na po kayo ng value ng CT, yung HN naman po, guys, that is the height of the building. And as you know, that the higher the building is, the greater the value of T you would be solving for. Okay? So yun, itry nyo na lang po, mag-substitute kayo ng kung ano-anong numbers dyan. The higher the height of the building, the greater the period you would be solving for. Okay? However, guys, this is rather not really inaccurate because hindi naman po nakakonsider dito, guys, yung geometry ng building nyo, and it is also not included here the properties of your columns, of your shear walls and the like. Okay? Thus, this is just an approximate value. However, I just want to disclaim that in the next videos in our sample problem, we would be making use of method A first. Unless mag-request po kayo ng method B and eigenvalue extraction method, I will be creating another video on that. Okay? So basically, those are the values that we would know or we should know. Ano pa ba yung mga na-miss pa natin? Okay, so the weight of the structure. So the weight of the structure, ito lang po siya. Nasaan na ba yung slide ko on the weight of the structure? Okay, so for the total dead load, basically, dead load lang siya. Okay, so total dead load, DL. However, guys, you have a special provision in NSCP that, for example, di ba DL, dead load nga yun, hindi nga kasama yung live load dyan. But in a situation we're in, the building that you are analyzing has storage and warehouses. Kapag meron pong storage and warehouse doon sa building nyo, ilagay nyo po yung 25% nila. So for example, that for your storage, meron pa pong 7.2 kilopascal. Just for pretend. Kunin mo po yung 25% niyan, idagdag nyo po doon sa pag-solve ng W. Okay? Also, where partition load is used in the floor design, you would be adding 0.5 kilonewton per, this must be square meter. So you would be adding 0.5 kilonewton per square meter. And you would also be adding total weight of permanent equipment. Okay? So suppose that you have machineries which you did not include for the dead load. Rather, baka sinama nyo po siya sa live load computation nyo. But if those are permanent equipments for the plants, by plants, hindi tanim, yung plants, planta, ganon, factories, the weight of those structures must be included to the value of W. Okay? So, in a situation wherein na lahat po to magkakasama sa building nyo, for example, you have storages, you have partition loads, and you also have permanent equipments, you would be adding them. Okay? So, from that, the effective W is dead load plus 25% of storage live load. Again, this is for storage and warehouse. Plus 0.5 kilonewton per square meter. Plus weight of what do you call this? Weight of permanent equipments. Okay. So there. So basically, nakompleto na po natin, and once that you already know all of them, direct sub na lang po siya. Just substitute them to these formulas. And take note, guys, that for this particular formula here, this is the design base shear. And as you can see here, the total design base shear need not exceed the following. So meaning that this is the maximum. And this is the minimum. And it is indicated here that in addition for seismic zone 4, the total base shear shall also not be less than the following. So this is another minimum, but this equation here must only be used if the building is located in zone 4. Okay? So solve for these 4 values, then piliin nyo na lang po kung ano po yung mag-govern. Okay? So once again, we have the maximum limit here, the minimum limits here, and of course, the design base shear. Okay? So once that you have already solved for all of them, mamili kayo na mag-govern, then basically that is already your base shear. Okay? So for our illustrative example, this is now for the next video. Okay? So there.